Right, we're here to study a little bit about friction, and friction forces are very common. They occur everywhere. Sometimes they can be beneficial and sometimes they can't. This little spinning top that I've just started spinning over here, starting to wind down and eventually collapse, primarily because the frictional forces, the friction resistance between the spinning point on the wood and my paper, and possibly some air resistance as well. So friction is responsible for a lot of difficulties in operation of machines. It requires a lot of energy to overcome, but it's also very helpful. It can be helpful if we need to walk places. We need to be able to create some frictional resistance so that we can grip with our shoes to walk, or we might use friction in brake pads, stop motion. So there's lots of useful uses of friction as well. Now friction was worked originally, or first research was done in the 1450s by Leonardo da Vinci, and da Vinci posited two laws of friction, and those two laws are fairly accurate. One was that friction was independent of surface area, so independent of the surface area in contact. And the second one was that friction was directly proportional to the force at right angles. To the direction of motion. So the harder you push things together, the harder it is for them to move of motion. Okay, so that was Leonardo's observations. They were developed on later on. Now we have approximately 4 laws of friction, and the first one is that friction always acts to oppose the direction of motion. That's the first. The second one is that friction can be summarized, or a frictional force can be summarized by a constant called mu, and mu_s stands for the static coefficient of friction multiplied by the normal force applied to the two objects that are in contact with each other. So normal force being a right angle force. So this coefficient of friction we'll talk about a little bit more later on. The third law is that friction is independent, as Leonardo posited. It's independent of the size of the contact areas, and it does depend on the roughness of the surfaces in contact. So they're the 4 laws of friction. And we can also say too here that when an object moves, so I'll try and find you an example of that somewhere around the place, but if we have a surface, like for example the top of this lid, this container, and we put another object on top of it, let's say this rubber, and as I'm lifting up the angle of this object, the component of the force that acts down the plane of the object will cause it to move. That type of frictional force that resists the motion of the object whilst the object is immobile and stationary is called static friction. Once the object goes into motion, the frictional resistance force is less than the static friction, and that's always the case. So static friction is always greater than kinetic or moving friction resistance to motion. That's something to remember. Okay, now it's just like I held up this object over here and I started to lift it up. You'll notice that just on its own weight, this rubber will reach a certain level or angle before it begins to move. Now at that point, just before it's about to move, the frictional force is at its maximum, and it's called limiting friction. So limiting friction is really the frictional force at its greatest. Now, limiting friction will occur between two objects on an inclined plane surface at a certain angle, and it'll be a particular angle for those particular two objects on the inclined surface, and you can measure it. And the relationship between those two objects, those two surfaces, is always related together through that formula that I just showed you up here. Frictional force is related to this coefficient of friction, which is unique for each different substance in contact. Now, one more thing to look at between this is that if we have an inclined plane here, and we create the inclined plane at an angle theta, we place an object on that inclined plane, the object will have a tendency to slide down the plane. Now, if the object has a weight force W acting through its center of mass, we can work out that here's the normal, so this is at a right angle force here. The W will split up into two components. One of them which we can be said to act at right angles to the angle surface. The other one will act along the line of the angle surface. Now, of course, friction always resists motion. We can expect a frictional force to be resisting this motion. So there it will be there. Call it Fr, frictional force. And we'll have a resistance to the weight force from the plane on the object pushing upwards. And that's called a normal force. And we'll call it N for normal force because it's at right angles or normal to the surface of the plane. Right, this angle theta over here will also be the same angle in here. Theta in here. Now, why is that? Well, it's a simple matter of organising some angles, and it's not difficult to show that that's the case. So these two angles being the same, this particular angle here is insignificant because when the object is just about to reach its point of movement as the theta increases, this angle here, or the angle at which the object is just about to move, is called the angle of repose. So it's the angle at which a plane has to be lifted up before the object will begin to slide on that plane. Now, if we look at this triangle that I've got sitting up inside here, these forces that resolve to W, this one here, using basic trigonometry, will be W sine theta. This force here will be W cosine theta, or cos theta. Now that in itself is useful for us, because we know that friction is related in this formula that we've used over here. If we were to play around with that formula and say Fr equals mu static friction times the normal force, we could say that the coefficient of static friction, mu s, is going to equal to Fr on n. Yeah? Okay, well, in this case on an inclined plane, Fr is going to be equal just before the object is moving, so it's on a point of moving. Fr will be at its maximum and will be equal to an opposite to W sine theta. So we could say that Fr is going to equal to W sine theta. At the same time, the normal force here will be equal and opposite to the normal component of W, which will be W cos theta. That means that put the two together, we can have mu s equals Fr on n, which equals to W sine theta divided by W cos theta, which equals to tan theta. So at the point of movement, when the angle of repose has been reached and limiting friction has been reached, then it is true to say that tan of the angle of repose equals the coefficient of friction. Okay. Now, armed with those facts, we can start to look at a little bit of a tough question here. And this comes straight out of Mr. Schlenker's textbook. Here it is here. Not quite that one. A little bit further on. Here it is here. So the question, let's see if I can bring it up a bit closer for you. Don't know if that's any clearer. Might be, might not. It says a machine of mass 500 kilograms being dragged up a ramp by a block and tackle is shown. The coefficient of friction between the machine and the ramp is 0.4, and typically coefficient of frictions range between 0.2 and 0.6. The ramp's inclined at 10 degrees to the horizontal. Show the angle between the rope, or determine when motion is about to occur up the plane, so we're at the point of limiting friction here, the angle between the rope and the ramp necessary to produce the least possible tension in the rope, and the rope tension at this particular instant. So we need the force T. We want to know that angle alpha, which indicates the angle of the rope. So that's our question. Okay. The first thing to be doing here would be to organise a free body diagram of what we've just done, that we just read about. So we've got, this is question 18/24 from Schlenker's Engineering Mechanics. I'll make this a little bit smaller. Organise a free body diagram, horizontal surface, angle surface, 10 degrees. You have an object or a machine, just draw it as a square. Centre of mass, you're going to have a tension on a rope pulling up here. It's going to make an angle alpha to a parallel surface with the plane. And we're going to have a normal force, which will always be the case, pushing up here at right angles. A normal force there. We'll also have a frictional resistance force. Now remember, this is dragging up the plane, so the frictional resistance force will be pulling down the plane because it always opposes motion. And we've got a weight component force which will act directly downwards here. Call it W. We know it's 500 kilograms, which means that W is going to equal to 5 kilonewtons. And looking at this, so that's about all the forces that we have at play here at the moment. Now, we could try and solve this analytically, but it'll produce some difficulties for us because we have some variables. We've got FR, we've got T, and we'd have to split these up into horizontal and vertical components, which would end up with quite a number of simultaneous equations that we'd need to solve. So to make it a lot simpler than that, we can use a graphical method, which will help us. And if we remember way back from the three-force theory, that if an object is stationary and it only has three forces acting on that object, then all of those forces must be concurrent, meaning passing through the same point. Now we've got four forces acting here, so we're going to combine two of these forces, and particularly we're going to combine the normal force and the frictional force. And we're going to say, for argument's sake, that those forces are going to combine together here into a reaction force which we'll call R. There it is there. And this will be the sum of the two forces N and FR. So added together will produce a reaction force. Now, if that's the case, we combine these two together, we end up with 1, 2, 3 forces, and they all must pass through the same point. So they're concurrent forces. So we can then create a diagram. But we need to work out what is the angle that this R makes with respect to the other forces, so that we can complete this this diagram. Now, to do that, we're going to take advantage of that little bit of information that we just looked at before. Remember, over here we calculated that the tan of the angle of repose is equal to the coefficient of friction. And we've been given what the angle of repose here, we've been given what the coefficient of friction is in the question. I think the question states that the angle of friction, or the coefficient of friction, mu s, is 0.4. So based on what we figured out before, tan of that angle, or tan of the angle of repose, I'm going to call it theta here. It's often used as phi, or that symbol there, phi or phi, but I'll call it theta for this sake. So tan of angle of repose is going to equal to 0.4, meaning that theta, or our angle of repose, is going to equal to tan to the minus 1, the inverse tan of 0.4, which equals to 21.8 degrees. Okay, so what does all that mean? Well, it means if we produce this normal down here like this, following that dotted line, like I've done, this angle here will be 10 degrees, just by geometry, simple geometry, the same as that. The angle of repose is the angle that our reaction force is going to make with the normal surface. So if we continue the line of action of the force up here, of R up there, the angle of repose will be this angle in here. And of course, just by simple geometry, this angle between these two lines will be the same as this angle down the bottom I'm showing you down here. That. So this will be theta, same as up here, which will be the angle of repose. And why is it the angle of repose? Well, it's the angle of repose because we've been told this object is just about to slip. It's just about to go. And although this angle of the plane is fixed, the fact that we've got an extra force here acting at another angle provides us with a changing some angle causing this object to start to want to move. And later on we're going to work out what this angle is. So at this point in time we know that that's 10 degrees. We know that theta is the angle of repose, and that's the angle that R, or the reaction, which is a summation of the normal and the frictional force, we know what that angle is. We've just worked it out down here using that formula we've worked out before. It's 21.8 degrees. So this is 21.8 degrees, making the total angle down here 31.8 degrees. Does that make sense? Okay, so if we know that this angle to the vertical, between R and the vertical, is 31.8 degrees, then and remember that of course the normal is not going to be, there will be a 10 degrees gap here. Yeah, then we can start to work out a simple graphical solution to this problem. And to do that we'll use a ruler, we'll create a vertical line, and I'm going to use a scale of 10 millimeters as 1 kilonewton. So there's 5 kilonewtons. So scale 10 millimeters equals 1 kilonewton. There's 5 kilonewtons, so there's my vector representing the weight force. I know that's going vertically downwards. Now I've got an angle of 31.8 degrees from which I'm going to run this reaction force. Now remember what we're looking for here, the question was asking for the angle that produces the minimum amount of tension up here. And it's a clever little trick we're going to do. But we know that the reaction force is going to be at 31.8 degrees from the vertical. So looking at the protractor, that's about there, 31.8 degrees from that centre. So I'll draw a line of action over here. So here's the reaction. We don't know quite what its magnitude is, but we do know that's its line of action. So I'll do it sort of a dotted kind of line. Call it R. This is W, which equals 5 kilonewtons. Now, there is going to be a tension T up here. There'll be a tension T on a rope, and it's going to act in such a way that we want it to be minimized. Remember, the question asks us to have a minimum tension. So looking at the diagram over here, we want a minimum tension involved. So T in length, the length of T, we know it has to go through this point, because it's going to be at repose. Therefore all the vectors will have to be head to tail, add up and come back to the same point that they began, creating a vector polygon. So at some point there's going to be a T that's going to intersect along here, cut across these lines and wind up pointing right here where my pen is. Now what would be the shortest distance? Well, it's a straight line, so it will be clear that a right angle is going to be the shortest distance between R and that point here. The reaction, which is a summation of the normal and the frictional resistance force. On this line of action, we know that's 31.8 degrees. We could work out what this is now, but we can just step it off. So this will be T when T is a minimum. And we can also calculate now R, because R has to join to this point. So we'll be able to, by measuring this distance, we can work out the magnitude of R, the combined reaction force between the normal reaction and the frictional reaction force, and we can work out T. So measuring T over here, it's about 26 millimeters, which according to my scale produces 2.6 kilonewtons. So that's the magnitude of T. And what will be the angle that T makes with the horizontal? Well, you can work it out using trigonometry if you want, but it won't be too hard for you to figure out that this angle of 31.8 degrees is going to be the same angle over here, 31.8 degrees. Now this angle, remember here we spoke about an angle of repose in our stuff, that's the angle at which the object, any object, starts to move if you lift the plane up and use the object's own weight force. Well, here's that angle of repose. There it is there. It's 31.8 degrees, and that's it there. So it's fair to say that when alpha equals 31.8 degrees, tension is at a minimum and the object is just about to slide. So it's interesting to note that little fact there, that no matter what kind of object it is, and no matter how big or small the contact surface is, that the object will want to slide when it reaches the angle of repose. And any rope that's used or attachment point will need to be at the angle of repose, will reflect that angle of repose. So I'm just thinking, double checking myself over here to make sure that, okay, I think I understand, yeah, alright. So this here, this angle here, is not the 10 degrees. This angle is actually 21.8 degrees. 21 point. Yep. Alright, so that becomes, when added to the 10 degrees, will produce the angle of repose. Yeah, that makes sense. So this angle here being 21.8, added to the 10 degrees, produces 31.6 degrees, 31.8 degrees, which is the angle of repose. Alright, and that's how we could answer that question, parts 1 and part 2. The magnitude I measured here, but you could calculate it using trigonometry, just using sine. Sine of 31.8 equals that over this, T over W. Work it out that way. Okay, thanks very much.